Krakow. Okay. I'm joining in from Mexico City. And if you guys want to say hi, please put in the chat just for everyone, the city you're joining us from. Very cool to see. Like when we have those live webinars that genuinely people join from all around the world. But yeah. And Pittsburgh. Is it Pennsylvania?
Yep.
Cool, very cool. But before we get started, a few housekeeping notes. So this webinar will be recorded and we'll send over slides and webinar replay to everyone who registered. So throughout the session, you can enjoy presentation from Adam and also think through questions. The best way to ask questions is in the Q&A section. If you see on the Zoom panel, there is this like little Q&A emoji. Please put in your questions over there. Or if you, for some reason, have questions after the session, right, you can always go to Platform Engineering Slack channel. And Adam is an active user of the channel. I would like so to be, but yeah, he joined before the webinar. Let me just put in the link really quickly so you know what channel I'm talking about. And yeah, feel free to join in, connect with the fellow platform and DevOps practitioners. We have a lot of interesting topics being discussed by our community overall. That's about it. We'll have 30-minute presentation. Adam has a lot of content, so really excited to and looking forward to it. And after it, we'll have 15-minute Q&A. That's about it. Adam, over to you.
Cool. Thank you for this introduction. My name is Adam Furmanek. I'm DevRel at Metis. And as you can see probably in a sec, I just started sharing my screen. So hopefully you can see the slides now. And in this session called Database Guardrails, New Age for Developers and Databases, I'd like to show you and discuss this paradigm shift that we are all experiencing now, how the world has changed and what we as like DevOps engineers, platform engineers, software engineers, we need to do in order to keep our world like maintainable and keep our databases like tamed a little bit. So this is what we are going to see. We'll see how the world has changed. We are going to see what challenges we need to face and we are facing today and how we can address them and how we can fix them. So let's jump straight to it because we have tons of content, not that much time. We used to be in a very simple world. Like 15 years ago, when we are talking about applications that we used to deploy back then, they were relatively straightforward from like the complexity of the deployment, maintenance, and like troubleshooting perspective. So generally, the application was something like SQL database, maybe a couple of nodes like EC2 workers or whatever else. We didn't have even cloud back then, and generally some like web server, load balancer, we would call it today. And that was it, right? That was the database, that was the application, that was the networking layer, and that's it. If we wanted to have another application deployed, well, it was completely independent, right? Deployed independently on the side, always good. When there was something wrong with our application, it was rather straightforward for us to figure out what's going on. We just needed to like go to application logs, which were living over there, or maybe go to the database and see what is wrong. That was easy. One DBA could deal with all of that. Software engineer could deal with all of that. Generally, we knew how to operate that. However, the world today is now way different. What has changed now is we moved on from like monolithical applications to microservices, from one database to multiple databases with well-defined bounded context as in domain-driven design. Now all the things are talking to each other. We do not have like one database in our application. One single application can now have like multiple databases, SQL, NoSQL, on-prem, cloud hosted, whatever else. We can have multiple different things for running our code. That could be like EC2 instance, that could be Azure function, that could be like some service bus, queuing mechanism, notification on the edge, whatever else. Generally, those things, those interconnected components, they can get very messy, especially when we are talking about troubleshooting. The world has changed, but we did not necessarily move on in terms of how to reason about the systems, how to troubleshoot them, and how to generally fix them. Because now when something goes wrong, we do not know necessarily first where the logs are. We don't have like easy way of figuring out the logs, figuring out the connections or relations between the components of our application. We do not know if the database is slow because, well, the query is slow, or because there are different like access patterns being exposed, or we deployed to different country and now things are going differently. So this has changed significantly, and we as software engineers, we changed the way that we deploy applications. However, we did not change the way we reason about them and we troubleshoot them. That is the problem, because when we start thinking about, hey, even a very simple application, this is the diagram I took from the internet. I Googled something like system architecture. This is one of the first images I found on Google, right? Even showing a seemingly system architecture poses like a challenge that there are so many different things that we need to understand in order to troubleshoot them effectively. We have load balancers, we have auto scaling, we have things running on the edge, we have different like storage solutions, databases, permissions, running this on Kubernetes, running this locally in cloud, yada, yada. And those things are hard. And now, because those things has changed, what we need to do in order to be able to find the issues and tame the complexity, we typically think about monitoring in the system, right? So we introduce monitoring, we introduce some like observability around the places, and we get dashboards showing us whether the system is healthy or not. The problem, though, is that when we think about those dashboards, they are completely unreadable in terms, okay, what is the actual reason of the problem? What's the actual issue behind the scenes? The problem is we do have dashboards showing us whether there is a fire or not, but they do not necessarily tell us where the reason is and how to automatically troubleshoot the things, how to fix them. And this is the point I want to stress. It's not something that only big corps like Fortune 500 companies are like facing. No, this is something that every application, every company nowadays is like facing day to day. We deploy stuff to cloud, we deploy stuff on Kubernetes, and we generally completely lose the idea how this works behind the scenes and how to manage this complexity. And this is what we need to change. We need a completely new approach, this new approach that will let us deal with this complexity and will let us handle all those issues in an easy manner. We need to have new tools, new processes, completely new approach. And this new approach we want to propose is called database guardrails. Because let's face it, most of the issues or the terrible catastrophic issues we may face in our application are around the database. If something goes wrong and the database goes bad, this is terrible because it results in data loss and other issues we'd like to avoid. So we need to make sure that we can reason about databases in better way. And it's the responsibility generally now, the responsibility of platform engineers to come up with new ways of managing databases and providing developers with the tools so that developers can finally own their databases. Developers need to be responsible for like the database performance and troubleshooting database issues, but we need to give them the tools. We need to give them the processes and the approach they can accommodate starting today. And this is what we want to do with database guardrails. So that's the idea, and let's see what can actually go wrong when we are talking about databases and how hard it is to reason about them. So let's see what breaks in the current world when we talk about the storage. So generally, all the issues with databases, they can be kind of grouped in like 3 different areas. First area is, well, code changes, meaning that, hey, we deployed new version of the application, so we started sending different queries to our database, and those different queries like get different data, different columns, different indexes. Obviously, things may break. This is one area. The other area is we have schema changes. So what we do is we change the schema of our database. We add new tables, create columns, change indexes. The problems that may arise here are something that affects the performance, affects the data quality, may result in data loss. But again, this is something completely separate from the previous area. But there is yet another part which we do not necessarily test, do not necessarily control with the tools we have and the processes we have, and which affects everything we do day to day. And this area we call query changes. And I don't mean here that we change the SQL statement that is being sent to the database, but instead, what I mean here is the query executes differently. It uses different indexes, accesses like different tables or views, and gets the data in different manner. This is something that we won't spot with our unit test. This is something that we won't notice with our integration test, because in those tests we focus on correctness, but this is something that will heavily impact our performance every day. And what's worse, those things may go wrong over time, meaning that our applications will rot over time. They will degrade performance just because we scaled our business out, we got more queries, we expanded onto more countries, we get more clients, more businesses, more tenants in our multi-tenancy application. So generally, those things like applications, digital applications can rot over time, despite the fact that we don't change them at all. So let's see actually what can go wrong with those databases. Let's see some actual examples, and then let's see whether our current processes and our approach actually prevents those bad things from happening and prevents bad code from going to production. So let's take slow queries. One thing that we may see is, hey, we have this aggregate root code user. We want to get the user from the database, so we get something like user with additional data like pages, text, location, yada yada. So this is the actual application code I was debugging once in my production system, and this JavaScript piece of code resulted in this SQL query being sent to the database. And this one query, even though it's just one single query for one entity, resulted in bringing in nearly 300,000 rows to the application, and then removing duplicates by the ORM, which took something like 25 seconds in total. Why did this happen? The problem is because we have so many joins in this query, the result is that we explode exponentially the number of rows that we take from the database, right? This query is super heavy when it comes to the performance. But the problem, and why it went unnoticed and reached the prod finally, the problem is that we won't notice the performance issues with our typical approach for testing and preventing the bad code from reaching production. In our unit tests, in our test databases, we have something like, I don't know, 10 rows. So even if we do this many joins, we will not get hundreds of thousands of rows being brought to the application. So we won't see the performance issues, right? Our unit tests won't notice there is a problem. How I had to fix that? In my case, the fix was rather straightforward. Instead of sending one query, I decided to extract the details separately in the application code and then merge the entity on the side of the application, right? So this resulted in sending something like 8 different queries to the database, but that was perfectly fine because each of these queries was crazy fast, finishing in microsecond. So in total, all of these was way faster than the previous query. And again, unit tests didn't even notice that I changed anything because those things were generally like correct and running the same data behind the scenes. But we can do similar thingy when it comes to readability. Let's say that we want to improve the quality of our code and increase the readability. What we do is, let's say we have boarding passes table, which has something like 8 million rows, okay? And now we might want to decide, okay, let's write a SQL query that uses CTE, common table expression. Oh, sorry for that. So CTE is basically kind of like named temporary table, which exists only for the span of the query. So we send the query like this. This is handcrafted example. What we do is we take the boarding passes, we take the ticket number and calculate the checksum of the ticket number twice and store it as double hash in this temporary table. This table is kind of not materialized. It may be heavily optimized by the engine. It's only like logical syntax for us to keep the query more readable. So then we take the CTE, we join it like 3 times with itself, and we look for the row with where ticket number double checksum is some specific literal. And we may also write exactly the same query like in this naive way without using CTE. So we take boarding passes, we join them 3 times, and we calculate the double checksum of the ticket number like directly in this where condition, instead of putting it like extracting the common code to the name table. And what you can see here is, if you know how CTEs work, those 2 queries are logically equivalent. They return exactly the same data. The problem is CTE runs for 13 seconds and the regular query runs for 8 seconds. So by improving the readability of the query, we nearly double the execution time and decrease the performance significantly. But our testing procedures won't catch that at all. Why? Because we focus on the correctness only. So we won't spot the issue is there. So by improving the quality of the code, we decrease the performance and didn't notice that. Moving on, we may have problems with like schema changes. We may add columns, and if we run select star queries against the table, then adding a column may decrease performance because now we get more and more data. But with schema changes, there is a bigger problem. When we add something like we add a column, change the column type, or do whatever else around the table schema, we may cause the table to be rewritten, meaning that we take because we can't apply the schema change in place, the database engine can't do that in place. What we need to do is we need to copy the data on the site, drop the table, create it from scratch, and move the data back. And this takes time. Schema migration may take minutes, hours, or in some cases, even months. I know a case from one of the companies that was running their schema migration literally for over a month. And seems like, okay, this is the cost, but do we know whether the cost is there? With our testing procedures, unit tests, integration tests, infrastructure as code, whatever else, the problem is we typically run all those test suits against the latest schema of the database, right? After all those migrations. So we don't even notice there is like a performance hit because of the schema migration taking time, taking hours. And during this migration, the database is down. Database is simply like unavailable just because it's changing the data behind the scenes. So again, seemingly innocuous change may cause database outage, and we can't catch that with our current procedures. Moving on, performance, indexes. When there is a query which is slow, we typically say, hey, just add an index. And we need to understand there are different types of indexes, obviously p-trees, indexes for JSON data, vector indexes for like vector databases, yada, yada. So we add that index and the performance is increased because the queries are now faster. I mean, read queries. But what happens when you tell your junior developer, hey, if you have a slow query, just add an index? You end up with this. You have so many indexes in your database that basically your performance drops significantly because even though read queries are now faster, then all the write queries, insert, update queries are like heavily impacted because you need to keep all those indexes up to date. And this is a problem. And the problem gets worse because you add those indexes over time, the performance degrades, like the effect accumulates over time. And at some point, you don't even know whether indexes are being used at all, because your query will return the same data no matter whether it uses an index or not, but the performance is different. And it may be that 6 months from now, so you added an index today, and 6 months from now, the index is not used anymore just because you changed the query or you changed the data distribution or data access pattern, right? So this is the problem. Our databases simply riot over time. And the problem with rotting databases is, it's very hard to spot that without proper tooling. Not to mention bugs, obviously. We may have bugs with the database engines themselves. For instance, one of the funny bug when we now think about that was Halloween problem. So on Halloween day, like October 31st, like 40 years ago or something like that, one company wanted to give a salary increase to their employees for employees who earned less than 10,000. Yes. So what they did is they run this simple query against the database, take all the salaries that are below 10,000 and increase them by 10%. The problem with that, though, is there are bugs in the databases, and their database was not protecting itself from the now we call Halloween problem. And in fact, it worked in the way that, hey, it was scanning the rows. It found a row, okay, salary is below 10,000, so it increased it. But because the rows were ordered on the salary, then this row moved in a place on the hard drive. So then the query was still going through the rows, found the same row again, salary was still below 10,000, so it increased it again. And effectively, after running this query, all the employees, their salary was at least 10,000 because this query updated that in a loop, right? So those are issues in the database engines that are very hard to track, and we may easily miss them with our today testing procedures. But let's switch gears a little bit. We may even have problems with added by ORMs. For instance, one of the problems is N+1 queries. So we have table aircrafts that have multiple seats. And if we send a query from application code like this, namely, we take all the aircrafts, and then for each aircraft in the loop, we want to take the number of seats. This may result in sending like N+1 queries, because first we ask for all the aircrafts, and then we ask for each aircraft separately, for the seats for each aircraft separately, which results in one query for aircrafts and N queries for seats, right? So this is terrible performance. This can be improved easily by reconfiguring our ORM into the so-called eager mode. So it sends the left join instead and gets all the data with one query. But the problem is, when you look at this application code, can you tell whether it's running in eager mode or lazy mode? The fact is, you can't. And if you have like tiny database in your testing environment, you won't see the problem at all because you have 10 rows at all. And you may say, okay, so let's switch the ORM to always send eager queries, right? But then we end up with the issue we had before. And this select star from the table with like 8 different joins, which resulted in like explosion of the rows. So generally, there is no silver bullet. There are other issues in ORMs. For instance, impedance mismatch. When we put the object-oriented model on the SQL, we end up with performance drops. Let's skip that actually because of lack of time, and let's focus on some other issue in the impedance mismatch domain. Let's say that we have the SQL database, and SQL database has a thing that is like called, obviously it stores strings like text, and it has a thing called collation. Collation is the way how we compare the characters in a string, whether lowercase letter is equal to uppercase letter and whatnot, what is the order of characters, and so on. And we can configure that on the database level. But how do we configure that in our string type in our application code? And what if we have heterogeneous applications? So one application talking to the database is written in JavaScript, the other one is in Python, yet another one is in Java. How do we make sure all those applications compare characters the same way? So generally, those are the things that we can't see easily, because those things are hidden. And ORMs, they add many more issues in terms of lack of visibility. For instance, transaction isolation level, transaction scope, who starts the transaction, who finishes it, who commits it. What about connection pooling? What about caching? What about like query hints? What about stored procedures and views and sharding, partitioning? What about migrations? Who controls the migrations in the database? Or if your ORM figures out there is a drift in the schema, is it going to change those things or not, or throw an exception? Those things are generally hidden by the ORMs, and it's very hard to reason about them when we look at our applications just like that. And the problem is we won't capture those issues with our typical test suite, because unit tests, integration tests, end-to-end tests, they focus on correctness, not on the performance. And the problem with them is the performance is something we don't see from these tests. But we can do something like load tests, you may say. Okay, I can just run load tests and see what the performance is and whether there's a problem. But the problem with load tests is, first, they are super expensive. They like take hours to complete. We need to have a fleet on the side. We need to pay for this machinery. We need to deal with privacy, with reproducing traffic, with GDPR, with anonymizing SSN numbers and other stuff. But the biggest issue with load tests is they happen at the very end of the pipeline. So you did your code review, you did your changes in the implementation, you even started pushing things through the CI/CD, and then you realize, okay, this won't work in production, and you need to start from scratch. This is way too late, way too hard to reason about, and we just can't let ourselves deal with databases this way. We need to have better solution for that. And the better solution we propose is called database guardrails. So what we want to do is we want to get the context of what is going on and what will happen in production before even leaving our developer environment. We need to know the context as early as possible, just like it was running in production. And in order to do that, we can get some modern solutions. For instance, we can get telemetry, OpenTelemetry, which lets us build the visibility in our applications, and in turn, application performance management, APM in short. So give a nice dashboard showing us what is going on in the application. However, the problem is APM will not give us the answer, what's the reason. It will only show us, hey, there is a problem here, but not the answer. And the answer, what's going on, is called observability. So the difference between monitoring and observability that we need to build is monitoring is about raw signals showing us, hey, there is a fire going over there. Observability will tell us this fire started here because you did that, just because you had a deployment last week. This is the solution we want to get. So let's now see how we can build that for databases. And for databases, what we want to do is first, we want to capture the signals. And this is something we can do with OpenTelemetry. So OpenTelemetry, what it does is it can allows us to capture the signals from our system, traces, metrics, logs, and other stuff. Thanks to the SDKs that OpenTelemetry provides, those SDKs we can use to instrument our application and build something that we call traces and spans. So let's say that this is our like microservices world. We have a checkout workflow. So we call the website, hey, I want to pay for this. Then this website calls some database. This database calls some, I don't know, queuing mechanism, notification service, and whatnot. So there is a workflow going throughout the system. Now, with OpenTelemetry, we can capture the human-friendly details of what's going on through the system. For instance, with explanation, when something started, what's the human-friendly explanation, some attributes of the operation, and build this nice graph of all the components talking to each other. So this graph is called trace, and each part referring to like every particular component of the system is called span. So we can build those spans showing us how these things flow throughout the system. And once we have that, once we have this OpenTelemetry, we can now focus on enriching that with our databases. So what we do is we want to understand what to observe in databases. So in databases, we need to understand how the queries are executed. So in order to do that, we need to understand the database engine. When we send a query, it typically runs through multiple stages, one of those stages being the planner. So the database engine takes the query like select star from table and plans how to execute this query. And this plan can be extracted using SQL code. For instance, if we have this query, we can prepend it in like PostgreSQL and other databases as well using explain keyword. And this explain will give us the execution plan explaining what is going to happen. And this execution plan, when we dissect it, we can see that it consists of like multiple nodes, and each node of the database execution plan explain what's the operation we execute. For instance, joins, for instance, scans, for instance, scanning indexes and whatnot. And most importantly, it also tells us how heavy this operation is. So it tells us whether this query is heavy or cheap. And now the database engine can generate multiple execution plans and compare them with each other to pick the cheapest one to tell what's the most optimal way to execute a given query. So now we have a plan. We have the OpenTelemetry. We can get the insights from our system. We have execution plans from our databases. If we now join these things together, what we can do is we can build database guardrails. And those database guardrails will allow us to prevent the bad code from reaching production and let us monitor the system end to end and automatically troubleshoot what's going on. So let's see that in action, because we would like to be proactive. Our world nowadays is much more complex than it used to be 15 years ago. Load tests are slow, load tests are very end in the pipeline, and we need to be proactive. We need to get the insights, what's wrong, what will break in our database the moment we implement the code as developers. And it's the responsibility of platform engineers to get those solutions, get those tools, and get this new approach, and then propagate it across the teams to finally let the developers own their databases. And Metis does exactly that. So let me quickly run through what we do, probably like to show you in like 2 minutes what we built, and then we will be able to wrap up this discussion. So if you onboard with Metis and you register your project, what we can give you, if there are 3 things we can give you generally. We can prevent your bad code from reaching production. We can give you monitoring and observability of all your databases, CI/CD pipelines, and whatever. And finally, we can give you automated troubleshooting, showing you what to fix and how. So let's say that when you onboard your application with Metis, you get recent activity tab that is showing you, hey, this is the REST API that you expose. Someone called this REST API and got this answer. However, when you take a look at what's going on behind the scenes, you can see this is the SQL query that was sent. If you want to get the query text, the actual query going to the database, you can get it. If you want to, get some visualization of the query, sure thing, you can do that. You can get like the statistics, execution plans, whatever you need. But the most important part is you get the automated insights telling you this query will not work well in production because it uses table scan, because it reads something like 16 million rows. And if you want to make it faster, you need to create index like this. So we provide you with the directly actionable insights showing you this is the problem, this is the solution. If you want to get understanding, feel free to do so. We provide you with all the details. But if you only want to see whether these things will work well in production, we got you covered. Similarly, we can cover pull requests and generally CI/CD of any kind. So for instance, we can analyze pull requests and provide the same performance insights, but we can also analyze things like schema migrations and tell you, hey, your code review, your pull request wanted to send those migrations. If you go to this like migration, then hey, maybe you have some issues, maybe you have some critical problems. Just be careful when running this migration in your production database. So we cover your developer environment and the CI/CD pipeline as you propagate the changes. But ultimately, when you deploy stuff to production, things may break over time. So we want to control that as well. So we provide a database-oriented observability dashboard. So the dashboard that, for instance, captures infrastructure metrics and the details of your databases, for instance, configured extensions and configuration keys or whatnot. But when we focus on the database itself, we can provide the actual actionable things about the database. So we can tell you, hey, those are the indexes you have. So for instance, we can show you, you have this many indexes, and maybe some of those indexes haven't been used like in the last 14 days, right? So we give you the history of indexes and maybe consider dropping this index because it doesn't have any usage, right? Or maybe we can capture the queries that are running in the database, right? So we can give you the history, hey, this is the query that has been running in the database. This is the duration over time. This is the number of calls. And hey, this is the insight. So this is how you can optimize the query now. And this thingy is something that is actually the database guardrails in the essence, right? You can now prevent the bad code from reaching the production. You can integrate with your source code. You can integrate with your CI/CD pipelines and whatnot. And even if you deploy stuff to production, you can then get a very straightforward and actionable observability telling you, hey, this query has changed since your last deployment. Your index is now not being used. Consider doing this and that. And this is how we can tackle all of that. So we integrate with the source code. So we want to have database guardrails that integrate with the developer application as developers like implement new things. We integrate with CI/CD because we want to prevent the things as they propagate through the pipeline, and we provide the full-blown true observability focused on the databases, not on like, you know, raw metrics telling you that CPU spiked. No, on things that are actually telling you this is the problem in your database. So being that said, the world has changed a lot. 15 years ago, we had one database, one DBA, all was good. Now we have so many microservices, databases, all things talking to each other. One DBA just can't cope with that. And platform engineers need to come up with new approach, new solutions, new tools, so that DevOps engineers and developers can finally own their databases and be proactive and have the checks pushed to the left as much as possible to get the actual direct actionable insights as early as possible. And this is what we need in the industry. This is what we call database guardrails, and this is what Metis covers for you. So being that said, it's time to call it a day. If you do happen to have any questions, feel free to ask them now, either in chat or wherever else. And yeah, I'm happy to answer them.
Nice. Just to some attendees had answers regarding the slides and the webinar replay, so we'll be sending over that tomorrow. Yeah, so you'll have that handy, the slides and the replay. But just to also to remind everyone, the best way to ask questions is in our Q&A section in Zoom. If you can put in your questions over there. Adam, you got some compliments in the chat. Brilliant webinar. So somebody is really looking forward to the replay and the slide. I don't know, usually we don't allow this for since it is the platform engineering webinar, but Tom is asking if you can show some screenshots of the Metis application.
Well, generally, I like all I showed you. I mean, in this part, this is something you can go and try out by yourselves now. We do have a very generous free tier, so all I showed you is available for free, so you can go and check that out. Other screenshots, actually, you can go find Metis YouTube channel, where I have multiple different videos walking you through this application and through the service and the integrations and whatnot. The playlist is called Metis in 90 seconds. So if you want to learn more, that's the perfect way of doing that. I'm happy to also share more materials, so feel free to drop me a line on platform engineering Slack in that case, and I'll send it over there. And I can see we have a couple questions on the Q&A. So first question is, what all database products does this support? So this is a very good question. What databases we support? We have official support for Postgres, no matter whether it's in cloud, on-prem, whether it's AWS on running on like Stackgrass. We are wrapping up our MySQL support, and hopefully we'll be able to announce that pretty soon. However, it's not like finalized yet. And then we'll work on NoSQL databases. So generally, I believe Mongo is gonna be our first choice, but we'll see what's that's yet to come. We support, as mentioned, both in cloud and on-prem. The things I showed you now is as a service. So generally, this part is hosted by us. However, the actual connector to your database and all the like statistic extraction and whatnot is running entirely on your end. So you can control that. It's open source. You can check that out. You can deploy that in the cloud, on-prem, whatever else. So this is what we support at this point.
Nice. Any other questions, guys? I see there are also some comments around the whole concept of guardrails for databases, which sounds to be interesting. And yeah, I don't know, maybe Adam, you answered all the questions in your presentation.
Apparently it seems so. If you do happen to have any other questions, or there is another one. As I understand, the explained plan is based on table statistics. What happens when the database imploded and the plans it produced are not accurate? So this is a very good technical question. How can we actually reason about the production database when we run the query against like the developer database, right? So local database. And generally, there are two things to that. First, we can capture the query that is being executed locally, and we can check, hey, what would happen if we executed that query against production? And if we now run into the case that the question asks like the statistics are bloated in production, then we will also signal, hey, your statistics are wrong. But the other thing we can do is we can take like statistics from production to your local database and like enrich the query plan and execution plan with those production statistics to tell you what would happen in production. Similarly, we can consider doing other stuff. For instance, let's consider if we add such index, would it improve the performance or not? And for instance, in Postgres, we can use an extension like HypoPG that can emulate the query being executed if there was an index like that. So generally, yes, one database may be bloated and statistics may be out of date. However, if we now take all the pieces from across the ecosystem of your application, then we can reasonably well tell you, hey, this is what's going to happen in production. So you don't need to run load tests. You don't need to deploy the stuff. You can get the answers, what if, when running things locally as a developer. So that is the idea. And this is how we can construct all of that to push those checks to the left, right? As I mentioned, load tests happen way too late. This, what I presented, we can do as early as like the moment the developer is, writing their SQL query or changing the application code. I hope that answers the question. And if you do have any other questions, feel free to drop me a line after this webinar. You can easily Google me. You can find me on Matty's page. You can also drop me a line on Platform Engineering Slack channel. And being all of that said, I'd like to thank you for attending this talk. Hope you liked it. Hope you enjoyed it. Feel free to take a look at our webpage and let me know how you liked it. And have a great day. Thank you.
You can see that you have some experience in leading webinars, Adam. Thank you.
Thank you. Yeah, you should say that.
Yeah, thank you very much, guys. See you next week. Next week, we are going to talk about how to design your repository structure for successful platforming. It's going to be with Kasper from Humanitech. So feel free to register and join in. But yeah, see the thanks for you, Adam. So thank you very much for the session. As I mentioned, we'll send over the webinar replay and slides to everyone. And well, hopefully see you next week, and hope you have an amazing end of the day or end of the week.